Hello everyone. Today I, Nishant Kumar, with my teammate Harish Kumar, will be talking about the third pillar, which is likelihood. So basically, we'll delve into the science behind likelihood and we'll have a better understanding what likelihood is all about. Coming to the content part over here, initially we'll be talking about the definition. Then we'll be talking about what is how likelihood evolved, and then how can we use as researchers the concept of likelihood. With that, we'll also touch upon the idea of whenever you surf on Google and other platforms, you'll find this question very common, like what is the difference between probability and likelihood, whether they are same, whether they are completely different, whether there is some kind of dependency between likelihood and probability. And with that, we'll come towards the explanation part, where we'll take a problem and we'll understand the different dynamics of it around the probability and likelihood thing. And at the end, we have quoted the reference for this PPT. Starting with, we have the likelihood definition. So basically, likelihood function, which is also named as likelihood, measure how well a statistical model explains observed data by calculating the probability of seeing that data under different parameter values of the model. Like what it is, like we have a complete data set. Based on that, which model would best fit that particular data set is what we can uh, understand using the concept of likelihood. It is constructed from the joint probability distribution of the random variable generated from observation. When evaluated on actual data points, it becomes a function solely of the model parameters. Now coming to the understanding, like let's taking account the Bayesian and the frequential statistics. In case of frequential statistics, like we know, likelihood is like the point estimate. Now relates with the point estimate thing. Likelihood is used to evaluate the plausibility of different parameter values based on the observed data, but it does not incorporate prior beliefs or update beliefs about the parameters. Like here, there is no prior knowledge kept into account. While in Bayesian statistics, although Bayesian statistics deal with the probability distribution or the distribution thing, while likelihood is more towards the point estimate part, but likelihood function plays a very crucial role in Bayesian statistics by updating prior beliefs to posterior distribution. Now we have to understand it quantifies how likely the observed data is given different parameter values as is combined with prior distribution to infer the posterior distribution of parameter. What it is, the posterior distribution depends upon the prior knowledge and also the current observed values based on different parameters values associated with it. Based on this, the posterior distribution is evaluated. Now, keeping again Bayes theorem into account. Now, when Bayes theorem was introduced, it updates the prior distribution with new data to obtain the posterior distribution. So what it is now, this particular equation will help you understand what I'm actually saying. Like the posterior distribution is totally dependent, is directly proportional to the combination of prior and likelihood function. So what it is now, we have this particular equation written where probability of the parameter theta, when we have the data given, is the posterior distribution, while the probability of theta with a given parameter is the likelihood function, and the probability of that particular parameter based on prior knowledge or prior distribution is what it is, and probability of data is the marginal likelihood. Marginal, what why we have used this, just to make this whole probability range between 0 to 1, or it's just a normalizing constant. Now coming to the evaluation of likelihood. Now, in the early foundations in the 18th century, what we found, David Hume's just there was an argument against miracle, so that the resurrection of Christ should not be believed as because it is against the law of nature. Now, when Thomas Bayes came and he introduced his Bayes theorem, Richard Price used this particular concept of Bayes theorem and challenged Hume's argument. He took 10 lakhs consistent observation of neutral events, non-natural and natural events like sunrise and other things. Now, the probability of a miracle occurring in the next trial was still not zero. It was still not zero. There was a possibility of miracle. So this was something using statistics, and the concept of likelihood was used over here. And based on this, they were able to counteract the argument which was imposed by David Hume. In 19th century, Gavril Gavret compared birth sex ratios for legitimate versus illegitimate births using Poisson distribution. And again, here also he used the concept of likelihood, but he didn't coin that particular term. He used significance testing and found out some kind of random variation alone is not sufficient for talking about the significant difference that was found in this particular study. Later, Francis Galton also did his sort of contribution in probability and correlation, but he didn't introduce the term of likelihood. And then Carl Pearson came in and he developed the method of movements and chi-square test, and which were the precursors to likelihood-based model fitting. But in the 20th century, in the early 20th century, it was the first time when Ronald A. Fisher first introduced the term likelihood function in hypothesis testing and parameter estimation. He formalized maximum likelihood estimation and introduced the likelihood ratio test, advancing statistical theory and rigorous frameworks. And now in the 21st century, we are using this likelihood function for multiple things, especially in the field of machine learning and algorithms. And now, how can we as researchers can use this particular concept in research? This can be used for multiple reasons, like for various reasons. First of all, for parameter estimation, likelihood function helps in estimating parameters of statistical model. By maximizing the likelihood function, researchers can find the parameter value that makes the observed data most probable. Secondly, model comparison, when we have a model A and model B and they have parameters as x1 and x2, now we can compare which particular model like best explains the data. Now, number three, we can talk about the model fit assessment. After fitting a model to data, likelihood function can be used to evaluate how well the model fits to the data. Okay. In Bayesian inferences, again in Bayesian statistics, the likelihood function plays a very central role by updating the prior beliefs to posterior distribution, which I've already discussed. Also, it helps in predictive modeling, like we have a model already prepared based on likelihood, and we know the possibilities of occurrence of this particular outcome. So, and then we can again use it as a predictive modeling tool as well. Hello, everyone. Today, I, Nishant Kumar, with my teammate Harish Kumar, will be talking about the third pillar, which is likelihood. So basically, we'll delve into the science behind likelihood and have a better understanding what likelihood is all about. Coming to the content part over here, initially we'll be talking about the definition. Then we'll be talking about what is how likelihood evolved, and then how can we use as researchers the concept of likelihood. With that, we'll also touch upon the idea of whenever you surf on Google and other platforms, you'll find this question very common, like what is the difference between probability and likelihood, whether they are same, whether they are completely different, whether there is some kind of dependency between likelihood and probability. And with that, we'll come towards the explanation part, where we'll take a problem and we'll understand the different dynamics of it around the probability and likelihood thing. And at the end, we have quoted the reference for this PPT. Starting with, we have the likelihood definition. So basically, likelihood function, which is also known as likelihood, measure how well a statistical model explains observed data by calculating the probability of seeing that data under different parameter values of the model. Like what it is, like we have a complete data set. Based on that, which model would best fit that particular data set is what we can understand using the concept of likelihood. It is constructed from the joint.
This brings us to the next aspect where we talk about the difference between probability and likelihood. For instance, let us say if you have a model and you want to talk about the outcome, then it is probability. On the flip side, if you have observed few outcomes and you want to figure out what model could have been used, then it is likelihood, which is also defined in this table, where likelihood is a measure of plausibility of different parameters given the observed data, whereas probability is for figuring out the possibility of an outcome of a random event. And we will also see the focus of likelihood, where it focuses on the parameters to figure out the statistical model, whereas the probability focuses on the events and the outcomes. And probability is calculated with a simple ratio of favorable outcomes by total possible outcomes, whereas likelihood is calculated using the likelihood function. And we already know probability always lies in the range of 0 to 1, whereas in case of likelihood, it will take positive values more than 1 as well. To better our understanding, let us take a real life example. Let us say you toss 4 coins, and given the situation, if you are talking about a chance of getting all 4 coins as said, then it is the probability. But let's assume you have observed that 4 coins, 4 outcomes as 4 heads. Then if you are talking about the chances of the coin being a fair coin, then you're talking about likelihood. So to depict this, we have also plotted a graph using Google Colab. And for the same example which we discussed, the if it is a fair coin, the probability of head will be 0.5. So getting a 4 head continuously, it will be 1 by 16, which is around 0.016. So that you will also see in the first section. And in the case, let us say it is a very biased coin towards head. So the probability of getting a head is always 100%. You will also see the likelihood is the maximum at 1. So this graph depicts how likelihood is being calculated for our example. We can also look into another example where here let us assume there is a model which predicts the price of a house given certain parameters. The parameters could be, for example, the number of bedrooms or the built-up square area of the house and multiple things. So here you will see two graphs. In the left side graph is a probability density distribution where it is the x-axis denotes the price of the houses and y-axis denotes the probability of that occurrence. And the area, the probability is calculated using as the area under the graph. So the whole area under the graph is 1, and we let us assume we want to find the probability of the house price being in between 60 to 80 lakhs, and it is 0.35. So given this probability graph, we already know the parameters of the mean and standard deviation. But in case of likelihood, let us say we have observed few prices of houses. We have already observed the outcomes. So now we are trying to figure out what is the best model that can fit here. So to do that, will tweak the parameters, that is the mean and standard deviation here with multiple values. So in this instance, we are using 3 values, and the outcome is same. So out of these, whichever is the highest value, that is the best fit model that will satisfy that will come closest to the actual model that exists. So this is how likelihood is helpful in a real life example. So that is the explanation about that. And this brings us to the final slide where we have taken references from. And I would also like to show you the code which we have used to generate the plot. Thank you.